Great, thanks for inviting me. So I'm speaking from Copenhagen. I'm going to talk about ergodicity and decision making, and it's an experiment that I did as part of a brain scanning project. Although I'm not going to talk about the brain data per se, but I'll talk about the behavioural data. So I'm going to just jump right in and start talking about gambles, but from a dynamical perspective. So this leans heavily on the work of Ollie Peters and Alex Adamu, who I believe are here. So we're going to define wealth at time t as just x brackets t, and we're going to think of a gamble. This particular gamble is a very simple one. We're going to toss a fair coin. If it lands heads, then your wealth is going to grow by 5 krona, and if it lands tails, your wealth will shrink by 4 krona. So R brackets T is just defined. It's a random variable defining the growth increments by which your wealth would change under this gamble, and this updates your wealth. So your wealth at the next time step is simply equal to your current wealth plus whatever the random variable was at the time. So whatever the outcome of the gamble was, that just additively changes your wealth. So the gamble has additive dynamics. It's probably the most common gamble studied in the fields I'm familiar with: psychology, neuroscience, economics, and so forth. And well, let's play the game tossing once per minute. So it's a very trivial game, as I'm sure you're aware. So we're just going to look at the ensemble average wealth of 1 million players playing this game. So the sum and track their wealth as time proceeds from 0 to 60 minutes. So there's some noise, but there's not that much noise because we're averaging over 1 million players. The purple line shows the expected value of the growth rate, which is trivial to calculate. That's just taking the ensemble average and taking n up to infinity. So the expectation value of the growth rate is 0.5 krona per minute. So as expected, this is a nice gamble to play. There's another way we can sort of look at this. We can take one player and follow them over a much longer period. So we now, instead of following them over an hour, we follow them over several days. So now we can calculate the time average of the growth rate by taking the time limit at infinity, and again we're going to find that the growth rate is 0.5 krona per minute. So it's probably no surprise that the changes in wealth for this game are ergodic. Ergodic, just under the definition that ensemble averages are the same as time averages. Now, for an agent trying to think about what gamble to take, computing the expectation value of the growth rate is informative because it tells the agent how their wealth might evolve over time. So now we can look at a different dynamic. We can look at multiplicative dynamics, same notation. Now the gamble is going to be determined by growth factors. So heads, your wealth grows by 50%, your total lifetime wealth. Tails, your wealth shrinks by 40%. And then now your wealth will update now as a function of this dynamic. So the growth factor is then multiplied by your current wealth. So we just say that this gamble has multiplicative dynamics. So these are just two dynamics. You can have many different dynamics, but we're just going to focus on these two just to illustrate some key points, and that sort of builds up nicely to the experiment. So let's play this game, and again tossing the coin once per minute. And this example, or all of these examples are stolen from Ollie Peters. So let's look at this in a bit more detail. So we're going to look at the ensemble average wealth of players playing over the 60 minutes. We're going to start with one player. So it's not really an ensemble average because it's just one player playing every minute for 1 hour. So there's a lot of noise, as you might expect. Let's do the same, but now we're going to take an ensemble average over 10 players playing the same game. Less noise, 1,000 players playing. And then we can take the limit, which would be an infinite number of players playing And that basically, unsurprisingly, as n gets larger, the ensemble, the fluctuations get smaller, and you hit the expectation value in the large ensemble limit. So, okay, so that looks like a good gamble to play, but you can't typically, unless you're a king or something, you can't typically access the average wealth of an ensemble of people, and you typically only have access to your own trajectory through life. So let's look at how these wealth trajectories evolve for individuals. So let's take this just one player and track them for 60 minutes. It's kind of noisy. Let's track them for longer, playing for a day. Track them for a year, playing once per minute for a year. And it looks like a pretty bad gamble, right? Maybe that person's just colossally unlucky. So let's just take 10 randomly chosen people playing the same game, again over a day, again over a year. And it's looking like the typical wealth trajectory for randomly chosen players playing is pretty poor. So what's going on? So, well, if you calculate the expectation value of this multiplicative gamble, then it has a expectation value of its growth factor is above 1.5. So you're getting exponential growth, which is why in the first instance we were seeing that exponential rise of the expected value of the wealth. However, if we switch to looking at the time average and we calculate the time average of the growth factor, that's below 1, and that reflects more the typical wealth trajectory of individuals playing the game. So these two are not equal. So this might not be necessary for an audience of mathematicians and physicists, but typically this is the point where the audience is totally confused, and they ask me, well, how can the ensemble average wealth increase while typical wealth decreases? And one intuitive answer is that, well, it's an inequality producing game. So the lucky few in the ensemble grow so rich that this dominates the average. Most people are losing money, but there's a minority that grow so rich that this dominates the average to pull the ensemble average up. So because the ensemble average is not equal to the time average, then the changes in wealth are non-ergodic by definition. And intuitively, well, if you're computing the expectation value when considering whether to play the gamble, it's not particularly informative of how your wealth will change over time. So how would you decide whether or not to play each of these gambles? So one principle you can think about is time optimality. So time optimality entails optimizing the time average growth rates of an observable you care about. We're going to just think about money, but you can apply it to any variable you care about optimizing over time. So maximizing the expected value we found was time optimal under additive dynamics, but it was ruinous under multiplicative dynamics. If you'd have played that multiplicative gamble, your wealth would have plummeted eventually. So I hope this shows that a good strategy for one dynamic can be a bad strategy for another. So this opens the question, well, how can you make time optimal decisions under different dynamical settings? So one approach, and I've just bastardized the lecture notes of Ole and Alex, but basically they specify a time optimal algorithm for maximizing the time average growth rate. So basically you need to specify the dynamic that you're facing. You then find the wealth transformation whose changes are ergodic under that dynamic. You then compute the expected value of those changes for the transformed variable, and by virtue of the ergodicity, you recover the time average. And then if you maximize that expected value, then you are, by definition, maximizing the time average growth rate of wealth.
If I could just interrupt for a second. So we have a question from Matej, who says, reading the Ergodicity economics PDF, I always thought, what actually are the other dynamics other than additive and multiplicative? And he's asking for real life examples.
So in Alex and Ole have a nice paper called The Time Interpretation of Expected Utility, where they consider a specific dynamic which would give you square root utility. I'm not sure how to describe that in words, but maybe they could interrupt. So basically, I mean, you can write down any dynamic you want, well, maybe they could answer that one.
Let's hold that off to the end.
Yeah, we can hold it off to the end. But there are other dynamics that you can specify that will result in different utility transformations. But I'm getting ahead of myself because I haven't talked about utility. So there is an equivalent way of thinking about this, which is perhaps more natural to those that think about economics, which is basically you specify the dynamic and then you find a utility function whose changes are ergodic for the particular dynamic. And then you compute the expected value of the changes in utility. And if it is the ergodicity transform, then that naturally recovers the time average growth rate. And then you maximize that expected utility. Now, the two are mathematically equivalent in the sense that they would lead to the same behavior and they would lead to the same outcomes and trajectories. So let's just flesh out what that would look like. So let's go back to our original additive dynamic. This is how wealth updates according to that additive gamble. Well, the utility or the transformation necessary to render it ergodic, or the changes in that utility ergodic, is just linear utility. So you don't really do anything to x because it already is an ergodic observable. Then you compute the expected value of the changes in utility. Well, that's just the expectation value of the changes in your wealth. And then you maximize expected utility. So here you're just maximizing the expected value. So it's kind of trivial. For the other dynamic, the transformation that renders those changes ergodic is the logarithmic transform. So then to maximize or to compute the expected value of changes in that utility, that would be the expected value of the changes in log of wealth, so just the log utility. And again, you maximize this expected utility. So this is interesting because it conflicts with existing theories in all sorts of interesting ways. As an experimentalist, I'm interested in theoretical disagreements, and the bigger, the better. And I've never seen a theoretical disagreement bigger than this. So basically, I'm just going to group some major theories or types of utility together: expected utility, prospect theory, and isoelastic utility. So, is utility stable under these theories? Arguably, yes, but it's distinctly not stable under time optimal utility because it changes every time the dynamic changes. Is utility idiosyncratic in the sense that can you have any utility function you want subject to the constraints of the theory? Yes, for these theories, but for time optimal utility, no, you can't. It's a very normative theory. It's literally you can only obtain the utility function that's time optimal. Now, of course, that makes it sort of psychologically slightly implausible. Of course, people are different, but as a idealized model, it's a very clear starting point. Is it calibrated to dynamics? Well, explicitly no for these theories. Explicitly yes for the time optimal theory. Can it maximize time average growth? Well, arguably no. If you present agents with different dynamics, by virtue of the fact that it has to be stable, it's impossible for the agent to maximize time average growth rates. And precisely yes for the time optimal model. So there are other models I can talk about that sort of complicate this picture, but these are the principal models that we compared in the following. So the question is, which of these theories best account for risky decision making under different dynamical settings? So we did an experiment to do this. It was in the brain scanner. We endowed subjects with lots of money, 1,000 kroner, that's about 125, 130 quid. We let them learn the dynamical effects of different stimuli on their wealth. So they observe these different stimuli, and they each have a deterministic effect on their wealth. That's just for them to learn what those stimuli do. And then they make active decisions between gambles comprised of those stimuli. So I'll unpack this in a moment. We then manipulate ergodicity of the wealth changes by switching between additive and multiplicative dynamics in the way that I've already shown you. And then we run some Bayesian methods to estimate parameters of utility models and perform model comparison to see which of these theories can best predict the data. Just a note to the physicists, you seem to be vulnerable to getting confused about fractals. Basically, the fractal it doesn't mean anything. We could have easily chosen cats and dogs. There's no inherent meaning to the actual fractal. So learning the stimuli in the passive phase. So basically, subjects can see their wealth in the middle of the screen. These numbers are just timings of events which are important for the neuroimaging. So time is progressing along here. This is a single trial. When the box comes on, you press a button, a wheel spins. This is just to keep subjects awake. And then crucially, a fractal image will come on, and it will deterministically affect your wealth. So every time you see this image, it will change your wealth in a deterministic way. And you'll see each of these many, many times, and you'll see there's a total of 9 different fractals to learn. So you're learning these for about an hour. And subjects' wealth are going up and down at quite a scary rate, because it's quite a lot of money. So subjects learn via experience. There's no explicit communication of what the fractals mean or what the dynamics are or anything. We just let them experience it. And then they have to decide between gambles in the active phase. So basically, this is the presentation of the first gamble. So it's similar to our example. So maybe that top fractal would represent a gain of 5 krona if the coin came up tails, and this fractal would represent a loss of 4 kronas if the coin came up heads. So every gamble is a fair coin gamble. So with 50% probability, you'll get this or this if you chose it. And they're all mixed gambles. So that's the first gamble, and then you're given a second gamble to choose against. So you can either choose this gamble or this gamble, each comprised of 2 images. And that's it. And you're doing this very, very rapidly. You're making a choice every 10 seconds. And what we do is we repeat the experiment under different dynamics. So we have a multiplicative condition and a additive condition. So you can see that the extremes are pretty hairy. So at one end, your wealth is shrinking by more than 50%. At the other, it's doubling by more than 100%. In the additive condition, you're at the worst end, you're losing 50 quid. Literally in just one event, you'll lose 50 quid. In another event, you'll gain 50 quid, and gradations in between. So what we're going to do is we use isoelastic utility.
Sorry? Just quickly ask a question about that. So is there a bankruptcy constraint?
No.
So you can go negative?
You can't. No, so you can't. So basically, they're filtered so that that wasn't possible. So we created bridges in the total such that you couldn't lose. You could end up with 0, but you couldn't end up with negative amounts.
So does that mean that the gambles you're faced with change if you get very poor?
No, I should say the gambles are realized at the end, so they're not aware of their current wealth or their current outcomes. So basically, if the sampled wealth, so we choose to realize 10 of the wealth. If that results in an extreme amount of money or extreme debt, then we sample again, basically. So the subjects know that they can't lose money and they can't win more than about 220 quid.
Are they allowed to decide how much to invest at each step?
No, it's all in on everything. So it's 100% leverage. That it's an interesting idea to allow them to leverage as much as they want, and then you could sort of look at Kelly criteria and things like that. Shall I proceed?
Yeah, go ahead.
Yeah,
sorry.
So we estimate the parameters of risk aversion. So basically, we use we estimate the parameters of an isoelastic utility function. So this is a simple, widely used utility function. It has one parameter, the risk aversion parameter eta. So if eta is below 0, then subjects are risk seeking. If it's above 0, then they are risk averse. If it's 0, then they have linear utility, which could be described as risk neutral. And if it's equal to 1, then they have logarithmic utility. So this is an interesting utility function to calculate because it contains the time optimal solutions. So by freely fitting these parameters, the time optimal model makes a prediction for what the parameter value should be under what condition. So we estimate this risk aversion parameter via hierarchical Bayes. So it's a Monte Carlo Markov chain method. It's hierarchical, so you do partial pooling over subjects. We have a sensitivity parameter that determines how stochastic or just how stochastic the choices are. Or another way to think of it is how sensitive their choices are to the differences in utility between the two options. And then the other parameter of interest is the risk aversion parameter, which I just described. So we're mainly interested in estimating each individual subject's risk aversion under the two different conditions and seeing how it changes. So just to recall, so the time optimality model predicts risk aversion should shift from linear to log utility. So it should shift from 0 to 1 if the time optimality model is correct. And if dynamics have little effect, then the risk aversion parameters should be relatively stable. So this is the risk aversion, the posterior risk aversion parameters collapsed over all subjects. In blue, we have the additive condition. In red, we have the multiplicative. The dotted line is the prediction of linear utility for the time optimal model, and the red dotted line is the log utility prediction of the time optimal model. So you can see there is some substantial spread within the conditions, but the modes of the distribution are surprisingly close to the predictions of the time optimal model. So recall the time optimal model it hasn't got any free parameters. It's just a specific prediction. And this, you can look at the single subjects, and there is some degree of heterogeneity, but every single subject substantially shifts or they all shift, increasing their risk aversion. And there's a huge Bayes factor for the hypothesis that they increase their risk aversion. There's another way to look at this, which is basically just to look at it on a heat map. So if we have risk aversion for the additive condition and risk aversion for the multiplicative condition, the time optimal model makes a specific prediction, which is that all agents should be at this intersection of linear and log utility. Obviously, there's going to be noise between subjects, so you kind of qualitatively you assume a cluster around this normative point. The other theories don't make specific predictions about what the utility function will look like, but they do predict that they will be relatively stable. So if they're stable, then they should be clustered along this diagonal. So in other words, you can have any utility function you want as long as it's relatively stable. And this is the actual data. So sort of qualitatively, it looks quite like it's corroborating the time optimal model. More quantitatively, you can look at the Euclidean distance of the maximum a posteriori estimates and look at the how far they are from each prediction. And in every case, for every subject, the time optimal model has a closer prediction to the actual data. But this is just parameter estimation. We can actually do formal model comparison where we take into account different complexities of models or different vaguenesses and so forth. So this is called a hierarchical latent mixture model. It's one large model which contains kind of three sub-models within it: a time optimal model, a prospect theory model, and an isoelastic model. And basically we have a model indicator variable which you can think of as it controls the degree of mixing of each of these that we need to best explain the data. So if prospect theory is the best model, then this variable will load highly onto prospect theory.
About wrapping up fairly soon, Ollie.
Oh yeah, I'm almost there. So the posterior probability of this can be interpreted as the posterior probability of the model given agnostic priors to begin with. We see strong evidence for the time optimal model over the other two models, and you can do things like the protected exceedance probability, which is the probability that each model is the most frequent in the general population, and again the time optimal model wins. So in summary, the parameter estimation and model comparison show pretty good predictive adequacy for the time optimal model compared to those we tested. We think it might be the first empirical demonstration of time optimal decision making and its dependence on dynamics. I'm not 100% sure, so there's a question mark there. Sort of to be provocative, I think we think it opens questions as to whether the most widely used theories of behavioral economics are adequate for explaining risky choice when ergodicity breaks. Obviously, this is just one experiment. It was only in 18 subjects, although it was highly powered within those 18. We want to replicate this to see if we can replicate it. We want to generalize it over different paradigms. It's quite an unusual paradigm. It's not really often seen in economics. And crucially, we want to test this over a wider range of dynamics because the theory makes very falsifiable predictions for a whole set of different dynamics. And more broadly, we think this motivates a need for incorporating ergodicity constraints into theories of decision making, and crucially, trying to falsify them. And just to advertise, we're interested in adversarial collaborators and students. The students don't have to be adversarial, but the collaborators are preferred to be for future projects. And these are the people that did the work. So these are the authors along here. And Finn and David did most of the heavy lifting. Thanks to London Math Lab for a lot of help with their theories and a lot of support, and a lot of skepticism from people on Twitter who've been remarkably helpful in improving our analyses. Thanks.
Thank you very much, Ollie. I think we'll run a little bit over and have about 5 minutes of questions if people are interested. And I'm going to just roll off with the first one, which is that. So I'm still a little confused about the way that you thought about utility maximization. So as an economist thinking about this, the way I would try and model it was that these 18 subjects coming in were trying to maximize some monotonic increasing function of the amount of money they walked out of the experiment with.
Yeah,
I wouldn't think about anything they cared about in the way that they got there. Is that what you set up and tested, or were you thinking about whether or not they cared about anything along the way?
So it's explicitly estimated on the trial by trial choices. So that would count as how you get there. So I think you're speaking to an issue that's quite often raised, which is you're taking whatever strategy is required to maximize the utility of your end wealth. Is that a fair characterization?
Yeah, so I would say I would expect people who were expected utility maximizers to use different strategies in the two situations. Now,
Yeah,
you still might be able to find differences in what came out at the end, because
yeah,
somebody with logarithmic utility would be more risk averse over the final outcome than
yeah.
somebody with linear utility. But it's my
So
understanding that somebody with expected utility would be using the Kelly criterion to try to.
yeah. So this is very much in line with some criticisms from Adam Goldstein, who's written a couple of blog posts about it, and we're collaborating together to sort of try and resolve this. So basically, he shows that, or he claims to show that if you have a particular utility function, then when faced with these different dynamics, you will behave as if you had different utility functions within the game, even though you've got the same base utility function.
That would be my claim.
Yeah. Okay. So, firstly, it's there's two things. One is that it's biologically and computationally implausible to do the necessary calculations, because the branching factors to simulate a head are just astronomical. So because the gamble space is huge, and because you never are have any of your gambles realized, there just involves colossal computation in order to actually try to calculate the end wealth. Secondly, even if you were able to do that, it's not a very specific model, because you're still unconstrained as to what your end utility function actually is. So you can still have any utility function, and then you've still got to calculate how many steps ahead they can calculate. But you can show it's implausible even to calculate ahead by one trial. But to do it effectively, you've got to calculate ahead by 300 trials. So it's not really a plausible model. You can, if you can't calculate ahead, then basically you then have the same, you express the same utility function as you have for your end wealth, basically.
Yeah,
and that's pretty much falsified by the data. Does that make sense?
it makes. I understand the words, but I'm going to have to read this more closely.
Yeah.
Alan looks at
So if you, I can send you his blog post, and then we reply to it in the latest version of the paper, which is just about to. We'll put the latest version on archive. And you can make your own mind up.
Yeah. Can I ask a quick question, which is, what precisely do the subjects know as it's going along? So they're sitting there making these gambles, and then the process underlying, whether it's multiplicative or additive, changes. You're changing that. So is this that they're just adapting to what's going on, or do they know anything about what the underlying changes are, or how the process is working?
So there's no explicit information. So they don't even know that it's possible that the dynamics can change. So the experiments are done on separate days. So within one testing session, the dynamics are constant. So it's unknown how they arrive at this kind of approximation of the time optimal model. Some subjects might figure out that it's entirely multiplicative or entirely additive just by calculating these things through. It's also possible that they just do it implicitly, but we sort of purposely didn't tell them anything in order to avoid any interference with any sort of lay theory that they may have about these dynamics, or about investments, or about all sorts of things.
If you can do this, if you ever do this with a larger number, or even with a number
we're planning on.
It'd be interesting to see, maybe you already published this, what the resulting wealth distribution is for the individuals at the end of the experiment. You only have 18 points.
But you don't allow for switches during one session. So in other words, what's happening to me is going to be the same during that session. So the process underlying is not changed during that time. Because there were experiments by Cohen at Princeton in his lab, where he actually had the thing changing as you were going along. So you really didn't know whether what was happening, the underlying process itself was changing.
Yeah, and perhaps that's more, well, on some scale that might be more realistic, because dynamics do change as a function of your wealth, but they probably wouldn't change on the matter of minutes. But yeah, it's a wide open question how you would learn these things, or learn different environments, learn the dynamics of different environments and how they switch. It's kind of fascinating question.
Well, I'm doing quite a bad job with time management here. We're running a little bit over, so I think we should say a big thank you to Ollie Hume.